Welcome to our lectures on flexible AC transmission system. We shall continue with our SBC versus we have discussed already STATCOM as well as SBC. Now, comparison of both the system we require to discuss in subsequent section. So, on the basis of the explanations provided by the various sections that we have already discussed, the linear operating range of the VI characteristics and the functional compensation capability of the STATCOM and SBC are similar. This is the actually the we can use STATCOM as well as SBC both, but there is a ifs and buts. The basic operation principle of the STATCOM is a converter based on the var generator acting as a shunt connected synchronous voltage source. Essentially, it is a voltage source and SVC actually the impedance. So, there is a basic philosophical difference between these two. SVC is a thyristor control reactor, thyristor switched capacitor operated as a shunt connected control reactive admittance. So, one is source, another is admittance. And thus, STATCOM have overall superior functional characteristics, better performance and greater applicational flexibility, and those do attainable with the SVC. We shall establish these consequences with this discussion. So, we shall continue with this presentation layout, that is what is the VI characteristics of SVC and VQ characteristics, that is reactive power handling capability of the both SVC and the STATCOM. Then how we will see that how it handles or ensure the transient stability, how fast it reacts, the response time, capability to exchange the real power, whether it can be added to compensate the reactive power with some add on or the retrofitting purpose, operation with the unbalanced AC system if there is a source unbalanced or due to some switching or anything, maybe inductance values is different, some load unbalance may also be there. Losses versus bar output characteristics and your physical size and the installation. These are the practical features we require to consider while you are, and another is basically the cost. I am silent about it, so you will conclude yourself what should be the cost. So, this is the voltage rating and this is the zero current rating, and you can see that it has a wide range of compensation. It can inject Cmax with any value of the voltage sag. So, voltage can be 0.2, 0.3, it can start and it can go to any voltage. So, this actually this reactive power handling capability is constant with the supply voltage. This is a STATCOM. So, STATCOM can perform wide range of operation while a disturbed voltage source, but in case of the SBC you can see that it will be linearly increasing with the voltage. So, it has a maximum voltage sag handling capability at around 0.1 and this is a transient rating, both will have a transient rating is less than 1 second. So, this is a VI characteristics of STATCOM and SVC. So, what we can conclude? This shows that STATCOM can be operated over full output current range at a very low voltage. Theoretically it is 0, but generally it is 0.2. Theoretically 0, typically at about 0.2 per unit of the voltage. So, it can compensate the reactive power when voltage sag has occurred. On the other hand, the maximum capacity of the inductive output current of the STATCOM can be maintained independently of the system voltage. That is the biggest advantage of the STATCOM. But on the contrary or contrast to the STATCOM, the SBC being composed of the thyristor switched capacitor and the reactor becomes a fixed capacitive admittance with a full output. The reactive power handling capability is totally depending on the source voltage. Thus, maximum attainable compensating current of the SBC decreases linearly with the AC system voltage, and thus the capability handling capability of Q also decreases. So, and this is this curve corresponds to the actually the Q and V, and essentially it is admittance curve. You can see that the reactive power handling capability of the STATCOM is VQ characteristics, and here it will be 1, and this is the transient rating, and this is actually the curve of the inductive pattern, and this is basically something like non-linear, but here you can see that it is linear. So, your operation is more predictable with the STATCOM, and this is a capacitive region and this is the inductive region. So, what we can conclude from these figures? VQ characteristics shows, in case of STATCOM, maximum var generation or absorption changes linearly with the system voltage. See that this changes linearly with the system voltage, but it is in quadratic in nature. SBC, the maximum output var decreases with the square of its voltage. So, it is in quadratic in nature. For this is what we can say, STATCOM is a superior to SBC, providing the voltage support under large disturbances. Since if there is a voltage fluctuation 20%, so it will be derated by 40% SBC, but there will be derating of the STATCOM will be only by 20%. The capability of providing maximum compensation current at reduced system voltage enables the STATCOM to perform in a variety of applications to achieve the same dynamic compensation as an SBC. We thus require a higher power rating. So, here in this case also STATCOM is also superior to compensate the more reactive power. Now, what else? STATCOM may, depending on the power semiconductor used, have increased transition rating in both inductive and the capacitive region, because you can, depending on the rating, you have a limitations on the switches, because in case of the SBC you are strictly using the thyristors, but you have actually the choice. You can use IGBT, you can use IGCT, you can use a GTO depending on the rating and the switching frequency. So, GTO is a slow device compared to the IGBT or IGCT. SBC has no means of increasing transient or the var compensation. Since the maximum capacitive current can draw is directly determined that by the size of the capacitor and the magnitude of the system voltage. So, thyristor is almost a passive device here. Maximum attainable transient overcurrent of the STATCOM in the capacitive region is determined by the maximum current turn off capability of the power semiconductor, but there it will be determined by the most of the cases by the capacitor rating and the voltages. The inductively operating region, the power semiconductor of an elementary converter switched at a fundamental frequency are generally naturally commutated. So, therefore, transient current rating of the STATCOM in the inductive current range is theoretically limited by only the permissible GTO or IGBT or IGCT junctional temperature. So, whatever the current rating for the devices, that will determine what should be the transient current limit. Thus, which would principally allow the higher transient rating and this range than the attainable capacitive range. So, it can handle more inductive power than the inductive power than the capacitive power. Now, let us come to the transient stability. We will consider the two machines model where actually you have put a shunt compensator at the midpoint. So, we have a angle Vs delta by 2 and this is the curve. Previously your curve was basically V square by x sin delta. Now, with the shunt compensation we have derived that this changes to V square by x sin delta plus V into I0 by 2 max into sin delta by 2. So, thus by changing the value of the current you can have a different curve. So, this is the case of it becomes 2 V square by x sin delta by 2 this curve and so on, you can change it. And but this is limited by the amount of the current. Actually you are supposed to get this curve, we have derived this equation, but essentially there is a limitation of the I0 that will be put by the devices mainly. The ability of the STATCOM to maintain the full capacitive power current at low system voltage also make more effective than the SBC in improving the transient stability, because it can you have a huge area, accelerating area to compensate. STATCOM increases the transportable power in the transmission system. So, this equation becomes 2 V square by x sin delta by 2, whereas the transmitted power is P shown against the transmission line angle delta for the usual two machine model versus the capacitive rating. This is the model. So, we can conclude that it can handle better transient stability. Now, for comparison, an equivalent P versus delta relationship shown for the also the SBC, where you have put the different value of x at the midpoint. The STATCOM, just like SBC, behaves like a ideal midpoint shunt compensator with P versus delta, and this equation becomes this. But there is a limitation until the maximum capacitive output power current IC max is reached. So, you are going to this is the ideal shunt compensation at the midpoint, and ultimately what should be the value of the BC max, that admittance, that will determine either you will follow this curve or this curve, and you can see that drop is very steep. Just go back to this thing. So, it is quite smooth and here it is quite sharp. So, for this reason you have a limiting condition, you should not go this point, you will drastically fall after that. So, what should be the conclusion from this observation? From the midpoint of the STATCOM keeps providing the maximum capacitive output current independent of the further increase of delta and the consequent variation of the midpoint voltage. The increase in stability margin obtained by the STATCOM over a conventional thyristor with SBC of identical rating is explained by the equal area criteria. The simple two machine system with the component of the STATCOM and SBC var rating can be connected at the midpoint, and let us see what is the conclusion. So, let us go back to the again our two machine model, and this is the case of the STATCOM equal area criteria. So, this one is an accelerating area and this one is your decelerating area. So, this is a margin, and you can change this margin by changing the value of IC max. Thus, we have already explained the equal area criteria, explanation of the equal area criteria. It is assumed that the system transmitted the steady state electric power P1 at an angle del 1 and is subjected to the fault for the period during which the P1 becomes 0, thus you got an acceleration power. During the fault, the sending end machines accelerate due to the constant machine output voltage, absorbing the kinetic energy presented by the shaded area below the P1 line and increasing to delta 1 to delta C. So, you can see that this will increase like that. So, thus what happened when original system is restored after fault clearing, the transmitted power becomes much higher than P1 due to the largest transmission angle delta C. As a result, the sending end machines start decelerating, but delta increases further until the machine loses all the stored kinetic energy. The recovered kinetic energy is represented by the shaded area between the P versus delta curve and the constant power line P1. So, this is your accelerating area, this is your decelerating area. Now, what happened to the SVC? Same thing, this is your accelerating area. The remaining unshaded area below the P versus delta curve and above the constant power line P1 provides the transient stability margin. So, this is your transient stability margin. From this figure, observe that transient stability obtained with the SVC is significantly greater than obtained with the STATCOM is significantly greater than the attainable with the SVC for the identical rating, because please go through this A. So, this is your margin and here this is your margin, since this curve is quite steep. As demonstrated by this section earlier, the attainable response time of the bandwidth of the closed voltage regulation loop of the STATCOM is also significantly better than SVC, because we have discussed that it has to wait for the cycles to start and all those things, but you can change the modulator index very fast. For this is the time constant Td, which characterized by the inherent transportation lag in the power circuit of the STATCOM and the SVC, is typically less than 200 microsecond to 350 microsecond in case of the STATCOM, but it is around 10 times or 15 times more in case of the SVC. So, it is actually 2.5 to 5 millisecond, that is actually the pi by 2 1 peak delay of SVC, because you may have to have a transient free operation. For this, you may have to wait total cycle, total quarter cycle. So, the typical transmission application, the STATCOM can provide a stable operation with respectable response over much wider variation of the transmission network impedance than is possible in SVC. So, of course, that we can say that in transient stability entity also STATCOM supersede SVC. Now, let us come to the next topic, that is exchange capability of exchange real power. Though we have considered that STATCOM, the shunt capacitor does not hold any real power. It is clear that STATCOM, in contrast to SVC, can interface with a suitable storage element if you can provide with the AC system for the real power exchange. That is, STATCOM is capable of drawing controlled real power from an energy source like large capacitor, battery, fuel cell, superconductor, solar cell, magnetic storage, superconducting material and its DC terminal, and deliver its AC power to the system. This potential capability provides a new tool of enhancing the dynamic compensation, and it also provides and improves the power system efficiency potential and prevent the power losses or loss of synchronization or the catastrophic failure of the power system. Thus, capability to exchange power will have these merits: real power, reactive power, and the real power exchange between the STATCOM and the AC system can be controlled independently to each other. This is one of the features we have seen, that 4-quarter operation of the STATCOM with a real with the power storing devices. Any combination of the real power generation and absorption with the VAR generation and absorption is achievable, and it is a 4-quadrant operation. 4-quadrant operation is possible. It should be noted that the short term dynamic disturbance and energy consumed by the devices, like switching resistors, switching losses of the devices, may be effectively used in place of the more expensive storage to absorb power from the AC system via STATCOM. Now, what about its performance, but in while handling the unbalanced power system due to load or due to source? For SBC, normally means that the control establishes 3 identical shunt admittance for each phase. So, while discussing, we have assumed that the system is balanced. With unbalanced system voltage, compensation current of each phase will be different, and it is possible to control the 3 compensating admittance individually by adjusting the delay angle of the TCR so as to make the 3 compensating current identical. We can of course change alpha and by changing it. However, in this case the triplet harmonic will be different in the 3 phases, and the normal cancellation through the delta connection would not take place. So, we have discussed that how to compensate the triplet harmonic while discussing SBC. So, if you have this unbalance into the system, so that method will not give any fruitful results. This operation mode thus would generally require an installation of the usually unneeded third harmonic filter. So, you have to put another bulky third harmonic filter because it is a low frequency. So, this filter will be very bulky. For this reason, individual phase control of the SBC in the transmission line compensation is rarely employed. Please note that point. The operation of the STATCOM under unbalanced condition is different from HBC. The STATCOM operation is governed by the fundamental physical law requiring that the net instantaneous power at the AC and the DC terminal of the DC voltage source converter employs must be always equal. Thus, you can have a unbalanced power or the balanced power, it does not matter. So, it can better handle the unbalanced. Assume that the DC terminal voltage of the STATCOM is supported entirely by an appropriately charged DC capacitor, and the loss of the converters assumed to be 0 for sake of establishing the case. With perfectly balanced sinusoidal AC voltage, STATCOM will draw the set of balanced sinusoidal current in quadrature with the system. They will 90-degree phase shift, but if it is not balanced, they would be not 90-degree phase shift, there is another phase shift. If the system become unbalanced, then what will happen? Then the alternated power component of the twice of the fundamental frequency will appear in the AC terminal of the STATCOM converter. Now, if the converter control ignores this AC voltage component, thus if it is operated to produce the AC output voltage as if the DC terminal voltage is constant, then the second harmonic component from the DC terminal will be transformed by the converter by the switching operation as a negative sequence of the fundamental, negative and the positive sequence of the fundamental components. As a result, it will draw the negative sequence from the fundamental component as well as the positive sequence and a third harmonic component from the source. Out of these 2 components generated in the output of the STATCOM as a result of the unbalance, the third harmonic is clearly unwanted. Please note that this will be circulating one. Whereas the negative sequence voltage generated naturally by the converter by the properly sized DC capacitor reduces significantly the negative sequence current that would otherwise be forced to flow the negative sequence system, and the third harmonic have no useful function. So, it does not provide any sinkage for the third harmonic. What will happen then? The overall loss versus reactive power characteristics of the STATCOM is already discussed. Both type of compensator have relatively low losses, 0.1 to 0.2 in the vicinity of the 0 var output. Losses in the both the cases increases with the increasing the var output, current rating increases, thus conduction losses increases. The loss contribution of the power semiconductor related to the component to the total compensator loss is higher for the STATCOM than for the SVC. So, please note this point. This is one of the demerits of the STATCOM. This is because presently available power semiconductor devices with the internal turn on capability have higher conduction loss than the thyristors, but we have now materials coming with the silicon carbide and all those things. There we may, this situation may change soon. Also the switching losses with the forced and the current introduction tend to involve more loss than the natural commutation. So, turn of loss will be there. It is reasonable to expect that historically rapid semiconductor development will reduce the device losses in coming years. That is what I was saying, that we may have actually silicon carbide device and other modern devices that may change this statement, whereas that losses conventional power components such as reactor are not like to change significantly. So, what we can say that STATCOM has a future. Thus, the STATCOM technological advantage probably will help to reduce the overall losses of the STATCOM more than the SVC. And what about the physical installation? STATCOM will generate the reactive power by using the semiconductor and thus have a small size. Large capacitor, large reactor with associated with the switch gear and protections and all those things, and used in the thyristor control SVCs, the system is bulky. As a result, the significant reduction of the overall size is about 30 to 40% is possible in case of the STATCOM. Small physical size of the STATCOM makes it eminent for suitable for the installation in areas while land cost is premium. That is also an important thing. Say you are putting a STATCOM in Bombay, so you require to consider it. For the application where anticipated system changes may require a relocation of the installation, that is also something you have to keep in mind. So, today it may be a load center, tomorrow that point may change. So, you may have to reinstall somewhere else. So, retrofitting and all those issues will have advantage on STATCOM. Thank you for your attention. We have concluded the actually comparison of the STATCOM and SVC.